This is Mrs. Pomerquay with the third video for Module 6. In this video, I'm going to be talking about stoichiometric calculations. The video will be a little bit longer than most of the rest of the videos I do for class because it will be quite a few calculations. So if you have to stop after watching a couple of the different problems, feel free, take some time to get through this material and learn it well. Stoichiometry, or the math of chemistry, allows you to make some calculations. You can calculate the amount of moles of a reactant or product if you are given the mass of a different reactant or product, or vice versa. Or you can calculate the mass of a reactant or product from the mass of another reactant or product. And I'll talk briefly about how you can use the volume ratios of gases to calculate masses or moles for gases. This little picture on the bottom illustrates a very important concept of stoichiometry, and that is that you cannot go from the grams of one substance, be it reactant or product, to the grams of another substance directly. There is no direct route from grams to grams. You have to go through moles and through your mole ratio to get from the grams of one reactant or product to the grams of or moles of the other one. So that if you can remember, you do not go directly from grams to grams, but you always go through moles, you will be well set up for being successful in these problems. So what's the first step in any type of stoichiometric calculation? Well, as I have said many times, you start with a balanced chemical equation because you need to use mole ratios to determine the relationships between your reactants and your products to answer the question of whatever problem you've been given. And if your equation is not balanced, your answer cannot be right. Also note that these balanced chemical equations represent ideal conditions, and when we're doing these calculations, that this may not be the numbers you would get if we were going to actually perform the reaction in the laboratory, but they are the predicted results under ideal conditions. So let's look at an example. Let's think about what happens when you react tin with hydrogen fluoride to produce tin fluoride and hydrogen gas. So this is our word problem. Tin fluoride is the type of fluoride found in some of the more expensive toothpastes. And so to write this chemical reaction, we have tin, and this is not one of the ones that you have to memorize, but tin, metal, so it's a solid, plus hydrogen fluoride, those are both nonmetals, that's a covalent compound, so the formula is told you in the name, and this is a gas, and it will react, because of course hydrogen is a gas in its normal elemental state, as is fluorine, if you remember those diatomics and the ones that you need to memorize that were gases. And so they produce tin 2 fluoride. This 2 in the parentheses we'll get to a little bit later in your modules, but it mainly is telling you that the tin has a +2 charge on it, and that since the fluorine has a -1 charge, this tells me then that the formula for this particular ionic compound for tin 2 fluoride will look like this, and then hydrogen gas, which of course is going to be a diatomic. So this would be a solid in your toothpaste, and this would be a gas. So to balance this chemical equation, really all you need to notice is that we've got a 2 here for the fluorine, or the fluoride ion, and a 2 here for the hydrogen, so we must need a 2 as the coefficient in front of our hydrogen fluoride. So moving on, the next step after you have balanced your chemical equation is to determine the known quantities, the things that are told in the problem that are things that the information you are given or information that you can look up using your periodic table. And I like to create a little problem table like this that has these different categories, that lists the reactants or products that I'm being asked to investigate, that tells me the mole ratio from the balanced chemical equation. I record the molar mass for each of the elements or compounds, and then the problem itself, the moles that are part of this particular problem, or the mass that is given in this particular problem. And so to fill this out, we are working with tin, So we put tin on one side as the one compound or the element we are investigating, and hydrogen fluoride on the other side. So those are the two things that I'm investigating. The mole ratio, looking at my balanced chemical equation, is 1 to 2. 1 mole of tin reacts with 2 moles of hydrogen fluoride. The molar mass, going back to the periodic table, we can look up that this one is 118.7, and actually I didn't look up hydrogen fluoride because I don't need to know that, since I'm only going to be looking for moles here, and I will be using the mole ratio to move directly from one mole to the other. So really the question that I'm trying to find out, the thing I'm trying to solve, is the number of moles here for tin, because once I have that, I can use the mole ratio then to give me the moles of hydrogen fluoride. So then I just need to solve the problem using the information I have for the molar mass and the grams, which is 75.0. So going on, I've transferred this information over. Going on to do the actual math, we would just set up, we've got 75.0 grams of tin, and we're going to multiply that by how many grams of tin there is in a mole. And so that, or not, well, we multiply that by our unit conversion fraction here, which is based on how many grams there are in a mole. And so you can set up your problem as multiplying these two together, or if you think of it as just dividing 75.0 by 118.7, whatever way works for you, as long as the problem has you canceling out your grams unit and leaving you with moles unit, then you will discover that you have made 0.632 moles, or you have 0.632 moles of tin. So we could carefully put this in the chart here, and then knowing what your mole ratio is, we've got a mole ratio of 1 moles to 2 moles. If our calculation tells us that with tin we have 0.632 moles, then of course to get our amount over here, all we have to do is multiply it by 2. So we multiply this by 2, and we find out that the amount of moles that we need for hydrogen fluoride to react with that amount, this many grams of tin, which represents this many moles of tin, is you need 1.264 moles. And then if you think about significant figures, you will note that we only have 3 significant figures available in the gram value. The counts of mole in the mole ratio don't matter, so that the answer, we would drop this last 4 and say that we had 1.26 moles of hydrogen fluoride would be needed to react with our 75 grams of tin, and that answers the question. In the previous problem, we were given grams of one substance and asked to calculate how many moles would be needed to react with it. This next problem does it in the reverse. The question is asking what mass of oxygen gas is consumed to produce a certain number of moles. And so, as always, you start with the basic step of balancing the equation. In this equation, you are reacting hydrogen sulfide gas, or it could be considered dihydrogen sulfide, but this is one of those compounds that is more commonly called just hydrogen sulfide. It breaks the rules. But hydrogen sulfide gas reacts with oxygen, it combusts with oxygen to produce not carbon dioxide, but sulfur dioxide and water. And this is not a balanced chemical equation. You can see that we don't have enough oxygen on the left in order to balance it. And so if you do some calculation counting out your various atoms to balance this equation, you will find that you need 3 moles of oxygen in order to make enough oxygen, but you also have to have 2 moles of everything else. So to balance this equation, we need to add those coefficients. And then you want to think about what are your known quantities. We are given a particular mole of sulfur dioxide, and we are asked to solve for the missing quantity of mass of oxygen. Incidentally, hydrogen sulfide is what gives the stinky smell to things like rotten eggs, or if you've ever had sulfur water. I used to have well water that was sulfur. And the smell of sewage and methane are all, that very distinctive smell comes from hydrogen sulfide, which is a toxic gas in large amounts. So let's fill in our known information. This problem is asking us how much oxygen is needed to produce a certain amount of sulfur dioxide. So those are the chemicals that we are working with. The mole ratio, you can see from looking at the balanced chemical equation, is 3 moles of oxygen is needed to produce 2 moles of sulfur dioxide. The problem tells us that we have, or what we want to produce, is 4.60 moles of sulfur dioxide. And so the question is what the mass is of the oxygen that we need to do that. So we have to figure out how many moles of oxygen we need to produce, and then use that to calculate how many grams of oxygen that would be. And then if you go to your periodic table and do some calculations, you can find that we have 32 grams of oxygen in 1 mole because this oxygen exists as a diatomic element. So you have to count the fact that each particle of oxygen in oxygen gas is 2 atoms. The next thing that we need to figure out then is the moles of oxygen. And notice that we are comparing moles to a mole ratio, and so we're comparing apples to apples, and this is a problem that is really very easy to set up as 2 proportional fractions and cross multiply. So if you think about it, we've got a mole ratio of 3 moles of oxygen compared to 2 moles of sulfur dioxide, and then we're given the amount of sulfur dioxide, 4.60 moles, and we're asked to solve how many moles of oxygen that is. And so the 2 fractions would be equivalent fractions. You can set them up this way as proportions and then do a cross multiplication where you'd multiply these 2 values together and these 2 values together, and you'd end up having 3 times 4.6 divided by 2, and so that you end up with X being equal to 6.90 moles. And so that's how many moles of oxygen you need to react with the 4.60 moles of sulfur dioxide. But the problem doesn't ask you about how many moles of oxygen, it asks you what is the mass of oxygen. So of course then you just take your 6.90 moles and you multiply that by how many grams, or 32 grams, of oxygen you have in 1 mole. And that will give you then the answer of how many grams of oxygen, the mass of oxygen you need to complete this reaction if you're trying to produce 4.60 moles. So if you do the multiplication and you consider for significant figures, you will get an answer of 221 grams. So remember, we had to go through the moles to get to the grams. And finally, a little more complicated problem. Given the reaction ammonium nitrate decomposing into dinitrogen oxide and water, the question asks how much of each product is formed when we have 45.7 grams of ammonium nitrate being decomposed. So that's the mass that we are provided with to start off with, and we have our compounds of ammonium nitrate and then dinitrogen oxide and water. If we look at the balanced chemical equation, because if you're given a reaction, it's given to you in the balanced form. So you can see these are our mole values taken for each of those particular compounds. The molar mass, going back to the periodic table, you would calculate that this is 80.1, this is 44.0, and of course water is 18. And then we're asked to figure out how much of each product, or what the mass is of each product. But we have a big blank space here in moles. And remember, you cannot go from mass to mass. That way is blocked. That is not the way to go. You always have to go through moles. So we need to figure out how many moles are there for each of these products, or each of the reactants and products. So in order to calculate the final masses of the other products of the products of this decomposition reaction, we have to go through the moles because we can't go from grams to gram, even though we have the rest of this chart is all filled out. And so our first key project is to figure out how many moles of the ammonium nitrate is made or is in this 45.7 grams. And so we'd have our 45.7 grams of ammonium nitrate, and you want to multiply that by the fraction, the unit conversion fraction, that would give you the amount of moles that is. And so we're comparing our grams per mole, and if you do this multiplication out, you'll see that you have 0.571 moles. And so that's the first step. And then you use your mole ratios to determine how many moles you have of your other substances. So the ratio between the ammonium nitrate and the dinitrogen oxide is 1:1. So of course you will have the same number of moles of dinitrogen oxide produced. And so if you just take that value and multiply it by its molar mass, 44.0, you will see that you have made 25.1 grams of the dinitrogen oxide in this equation by decomposing 45.7 grams of ammonium nitrate. And then you could just go a step further and say, look, I have twice as much moles, and so I could just double the mole value here. But just to show you another way of solving this problem with the mole ratios included in the equation, I want to not do that, just let you know that you could do it that way. But you also could set up a situation where you have your 0.571 moles of the ammonium nitrate and multiply it by your mole ratio. And since this has ammonium nitrate in the numerator, we want to put the mole ratio of ammonium nitrate in the denominator, so they will cancel, so that the 1 will go here and the 2 moles of hydrogen will go in the numerator. So this allows us to, not of hydrogen, of water. This allows us to cancel out our units. So this is our ammonium nitrate in the numerator here, and so we have to have ammonium nitrate in the denominator here. So it is very important that you keep track when you're doing multiplications with mole fractions. You have your compounds there as a unit to be canceled so that you have your fraction arranged with the proper mole ratio order. Not 1/2, but 2/1. And then you could just keep on going and multiply that by the 18.0 grams per mole for water, and that will cancel out the mole units, which then gets you to your answer at the very end, which being grams of water that would be produced. And if you go ahead and do the multiplication here, you will find that it's 20. This is not a very good writing here. 20.6 grams of water is the amount of production here. So we've got our 25.1 grams of the dinitrogen oxide, and then 20.6 grams of water are the masses of the products if you decompose 45.7 grams of ammonium nitrate. And so stoichiometry has allowed you to predict what the results will be of this decomposition reaction. And this is the type of use that the stoichiometry calculations are put to by chemists, predicting amounts of products or predicting amounts of needed reactants. When it comes to gases, we have a sort of a special case. A scientist named Joseph Gay-Lussac found that gas volume ratios in reactions that involved only gases were in whole numbers, which suggested that the volume ratios were related to the stoichiometry coefficients. And so Avogadro went on to hypothesize that equal volumes of gases at the same temperature and pressure have the same number of particles. And actually, a fact that you don't need to memorize, though the honor students will, is that 1 mole of any gas at what is known as STP, and we'll run into that later in Module 12, standard temperature and pressure, 25 degrees Celsius, which is warm room temperature, and 1 atmosphere, the amount of particles in 1 mole occupies 22.4 liters, which is roughly the space taken up by a 14-inch diameter beach ball. So in that amount of space, you have 1 mole of any gas. The density of that gas will be different because the actual molar mass of individual particles still is very much dependent on protons and neutrons, and so the atomic masses of the individual particles is different. The density of the gases will be different, but the volume of gases at the same temperature and pressure are the same, and a mole occupies 22.4 liters. So because of that, you can do something special with equations when you're only working with gases. You can go directly from volume to volume and not have to think about moles or grams. So to give an example of that, we have this problem for the combustion of propane. So propane, and again this is a given problem so it's already balanced, propane reacts with oxygen and then produces carbon dioxide and water. And so the question is, what volume of oxygen is needed if you're going to combust this volume of propane, 0.650 liters. And so you just need your mole ratios to solve this problem, because we can go directly from mole ratios to volume. So we've got propane over here, C3H8, but I'll just write out the word propanes, and then oxygen. And propane, the mole ratio is 1 to 5. And so then you have, what's the volume that's given to us in the problem? Well, the propane volume we're starting with is 0.650. And so the propane, or the oxygen volume, of course, is just going to be 5 times that, because where mole ratio is saying the amount of oxygen needed is 5 times the amount of propane, and since the volume stays the same with gases when they're at the same temperature and pressure, that we can go directly from mole ratio to a volume amount. So if we multiply 5 times 0.650, then it tells you that we're going to need 3.25 liters of oxygen in order to fully combust the 0.650 liters of propane. So if you're only dealing with gases, you can go directly from coefficients and volumes through the mole ratio. But if you've got a problem that does not deal with gases, you do need to do those more complex stoichiometry calculations. So hopefully this video will help you with the math of chemistry, and we'll be working with these in class to try to make sure that everybody gets a handle on how to work with these numbers.